everyone, welcome to Power Electronics lecture series. In today's video, we're going to take a look at input performance parameters of rectifiers. So let's get started. So in our previous video, we spoke about output performance parameters. But here, input performance parameters are primarily focusing towards harmonics. Now you might ask me a question, how is harmonics related to input performance parameters? I'll give you a detailed overview here. Let us say we have a sinusoidal supply of AC signal that is given to a step-down transformer. This step-down transformer induces an voltage at the secondary terminal, say that to be equal to Vs1. And let Is be the corresponding current RMS value of secondary current, and Vs1 is the RMS value of secondary voltage. These two are given as input to rectifier. The rectifier will convert AC to DC, and DC output is obtained at this point. So AC is converted to DC with the help of a rectifier circuit. Now what may happen is, because of the nature of load that we are employing in that particular circuit, there are chances that the source, that is with respect to the secondary side of the transformer, may have harmonics induced in them. So over here, there are chances that harmonics are induced in them. So what is harmonics? The deviation with respect to the sinusoidal signal is what we consider it to be harmonics, isn't it? So now let us consider this particular waveform. This is the secondary voltage Vs, and this is the secondary current Is. Now you might be having a question, as the secondary voltage is sinusoidal, but why is the secondary current not sinusoidal? Let us say I have assumed an inductive load at the DC terminals, at the load terminals over here. So there are chances that the secondary current Is can also be a square wave. And when the secondary current, that is is a square wave, what happens? There are harmonics induced in them, isn't it? Because they're not sinusoidal in nature, and there is a deviation with respect to the shape of the signal Is, and we need to resolve that Is into sinusoidal nature. And this sinusoidal resolvement is nothing but Is1 over here. Is1 is basically RMS value of fundamental component of secondary current. Please note this point. So basically, through Fourier analysis, what we will be doing, we will be resolving non-sinusoidal signal, that is Is, into Is1. And because of this, harmonics that are induced due to the deviation in the signal, we will be focusing towards harmonics for input performance parameters. I hope this point is clear. So first, let us make a note of what these components are. Vs stands for RMS value of secondary voltage. So these are very important parameters because we will be considering this only in our parameters formulas. So we will directly be taking these values. So please make a note alongside me. Is basically RMS value of secondary current. So RMS value of secondary current. And what about Is1? Is1 is basically the RMS value of fundamental component of secondary current. So make a note of it. This is going to be the resolved component using Fourier analysis. Fundamental component of secondary current. And phi1 over here, which I have not shown, phi1 is basically the displacement angle, and it is given as the angle difference between Vs and Is1. So it is called as the displacement angle. Very, very important point, and these are very, very important in the parameters, and you will be seeing that in my upcoming points. Having observed these points, now what we will be doing is we will straight away go to the performance parameters. Active power input or active power drawn by the converter is given by a simple formula, that is active power input is given as V. Usually we know active power is given as Vi cos phi, isn't it? So over here in terms of secondary voltage Vs, Is1 is the component that we are going to resolve, and cos phi 1. So phi 1 is basically the displacement angle that we had seen, isn't it? So active power input can also be represented as PI. The second component that we are going to see is reactive power component. Obviously, the reactive power input is given as Vi sin phi in general, isn't it? So can we write the reactive power input in this case to be equal to Vs Is1 sin phi 1, and this is represented as Qi. I hope this point is clear. Now what is input power factor then? The input power factor is basically given as the ratio of active power drawn by the converter, that is Pi divided by input secondary volt ampere. So be very careful with this point. Input secondary VA rating. Basically Pi is given as Vs into Is1 cos phi 1, isn't it? What is input secondary volt ampere? It is given as Vs into Is. So what will happen? Vs and Vs will get cancelled out and we will be left out with Is1 by Is into cos phi 1. So the power factor, input power factor, is basically given by the formula Is1 by Is in terms of cos phi 1. Very, very important formula, because in most of the converters we will always be finding the input power factor. The next important parameter is input displacement factor. So the displacement factor, represented as df, is given as cos of the fundamental displacement angle, that is phi 1. So this relationship is important. So they may ask you to find the input displacement factor by giving the Vs and Is1 values, and from there you have to find the value of phi 1, and based on that you will have to find the value of df. So this is one of the most important relationships. The next important formula, or the relationship that we are going to take a look at, is current distortion factor, represented as CDF, and it is the ratio of Is1 by Is, that is RMS value of fundamental component of secondary current to the RMS value of secondary current, isn't it? Now we know Is1 by Is into cos phi was the formula for input power factor, isn't it? So we had Is1 by Is into cos phi 1. Can we rewrite this formula as Is1 by Is can be substituted as CDF, and can we write cos phi 1 as DF? So this is a very important relationship. Input power factor can be expressed as the product of CDF and DF respectively. So they may give you two parameters and ask you to find the third parameter. In that case, you can directly use this particular formula. So make a note of this formula separately. So I'll be making a note over here. So this is a very, very important relationship. So make a note of this separately. Very, very important. Now we're going to take a look at our next parameter, that is total harmonic distortion. THD is given by the fundamental definition, that is, it is the difference between the square of the Is square minus Is1 square whole divided by Is1 square. Now when you are further simplifying this particular expression, you will be getting Is square whole divided by Is1. So you can write Is by Is1 whole square minus 1. Is by Is1 can be written as 1 over CDF, isn't it, from this particular expression? So THD can be represented in terms of CDF. That is what we are trying to prove over here. So 1 by CDF whole square minus 1. So if in case they ask you to find the total harmonic distortion and they give you the current distortion factor, it will be a straightforward substitution, isn't it? Now the final parameter that we are going to see is crest factor or peak factor. The crest factor is given as the ratio of peak value by RMS value. That is nothing but the peak value divided by the RMS value. The peak value In terms of current, if we are talking, it can be represented as ISP, and RMS value can be represented as IS. So this is the crest factor relationship. So these are the 7 important input performance parameters that you need to make a note of, and this will be very, very important to solve n number of numericals and to analyze and compare different converter circuit with respect to the performance parameters. In case you have any questions with respect to this video, feel free to reach out by typing your questions in the comment section below. Thanks for watching. Keep supporting. Thank you.